Let's practice more now with the idea of sigma notation to make sure we're really comfortable with it. We're going to work through examples 2 and 3. In example 2, we want to write out the first 4 terms for each of the following series. Our first series is the sum from n equals 1 to 10 of 2n plus 1. So we're just practicing here expanding out the sigma notation, making sure we're comfortable with this. So I start with n equals 1. I'm going to insert 1 for n. So I have 2 times 1 plus 1. And then next I increment up, now n equals 2. So my next term is 2 times 2 plus 1. And then 2 times 3 plus 1. And then one more term, 2 times 4 plus 1. We could, if we wanted to, figure out what that is numerically. In fact, this whole sum, since we're only adding up 10 terms here, this is finite. This series converges, but we won't worry about what value it converges to here. This continues on. We could actually write the last term here. The last term would be when n equals 10. So the very final term here would be 2 times 10 plus 1. And we could work through to add up all these numbers, but this is the expanded version of this sum. It's not really necessary for this problem, but let's just simplify a little bit because I want to point out a pattern here that we'll notice in these different terms. So the first term we have 2 times 1 plus 1. 2 times 1 is 2 plus 1. That's 3. The next term, 2 times 2, 4 plus 1 is 5. Then 2 times 3 is 6 plus 1 is 7. 2 times 4, 8 plus 1 is 9. And this ends at 2 times 10, 20 plus 1. It ends at 21. Notice here in the expanded version that there is a difference of 2 between each of these terms. 3 plus 2, 5. 5 plus 2, 7. 7 plus 2, 9. Where does that difference of 2 between the consecutive terms come from? It comes from this 2 right here. Multiplying by 2 in the sigma notation will give us a difference of 2 in the expanded form. That's something that we'll see in a future example. Let's look at part B. For part B, we have the sum from 2 to infinity of negative 1 raised to the n plus 1 divided by 3 to the n. So I'm going to write out the first 4 terms. Now the index starts at 2. So each of these n's I'm going to put in a 2. So negative 1 to the 2 plus 1. 2 plus 1 is 3. Divided by 3 to the 2, 3 squared. There's my first term. I just plugged in n equals 2. Now the index goes up by 1. So now I'm going to plug in n equals 3. So I do plus. Negative 1 to the 3 plus 1 is 4 over 3 cubed. Plus negative 1 to the 4 plus 1, 5 divided by 3 to the 4th. One more term, negative 1 to the 6 divided by 3 to the 5th. We can see how increasing the index values changes these values in the expansion. The 2, 3, 4, 5, those are the different values for n incrementing up. This is an infinite series, so this continues on to infinity. Just for practice here, I want to take one step to simplify. I want to think of these negative 1 to the powers. When I have negative 1 raised to an odd power, that's negative. I have negative times negative times negative. That is negative. When I have negative 1 raised to an even power, it's positive. So I get this flip-flop of signs here. Negative 1 cubed is negative, so negative 1 over 3 squared. And then negative 1 to the 4th is positive, so we'd have 1 over 3 cubed. Negative 1 to the 5th is back to negative, so I have minus 1 over 3 to the 4 plus 1 over 3 to the 5. The next term would be minus 1 to the 3 over 6, and the pattern continues. So when we have these negative 1's raised to a power, we get this flip-flop, negative, positive, negative, positive. That's an important sort of a pattern that we're going to see quite a bit. Take a look at letter C. Here we have the sum from 0 to infinity of x to the n divided by n with the exclamation mark. This is called a power series because it has this variable x in it, and we'll learn more about power series as we continue. So this is a power series, whatever that is, and the x just stays as x. So we're going to have an expression with x. The index is still n. Now we need to talk about this n exclamation. This is called n factorial. So before we expand out some of the terms here, let's first focus on this n factorial business. So this is n factorial. And factorial tells us to multiply all the numbers from 1 up to n. For example, 4 factorial is 1 times 2 times 3 times 4. 3 factorial is 1 times 2 times 3. 2 factorial is 1 times 2. 1 factorial is 1, just 1. And we can expand some of these out. 1 times 2 times 3 times 4. Well, let's go the other way. 1 is just 1. 1 times 2 is 2. So 2 factorial is equal to 2. 3 factorial is 1 times 2 times 3. That's 6. 4 factorial is 1 times 2 times 3 times 4. Or we could think of this as 1 times 2 times 3. That's just 6 times 4. So 6 times 4, we get 24. We could do 5 factorial. 5 factorial is 1 times 2 times 3 times 4 times 5. We've already figured out what 4 factorial is. That's 24. So we would have 24 times 5. 24 times 5 is 120. So these numbers are called factorials. And we just take a whole number and multiply all the numbers from 1 up to that whole number, and that's a factorial. So we have 5, 4, 3, 2, 1. We could continue 6 factorial, 7 factorial. Let's look at 0 factorial. 0 factorial, we start with 1 and we multiply all the numbers from 1 up to 0. That seems weird. So by convention, we're going to say that 0 factorial is 1. This is counterintuitive. We'd like to think that 0 factorial is just 0, but I like to think of 0 factorial as an empty product. What do we multiply by to not change anything? Well, we would multiply by 1 to not change anything. So that might not be a super satisfactory answer, but 0 factorial by convention, we choose to equal 1. It is not 0. So now that we've seen the idea of factorials, let's go ahead and expand out this power series. We start with n equals 0. So my first term is x to the 0 divided by 0 factorial. And then in n increments up, so x to the 1 divided by 1 factorial, plus x squared divided by 2 factorial, plus x3 divided by 3 factorial. There are the first 4 terms. And let's just simplify this a little bit. This would continue on to infinity, but let's simplify. X to the 0 is 1. And 0 factorial we just said is 1. So I'm going to have 1 over 1. That's just 1. So my first term here is 1. X to the 1 is just x. And 1 factorial is just 1. So my next term is just x over 1, which is x. My next term is x squared divided by 2 factorial, and I'll just leave it in that form. And then plus x cubed divided by 3 factorial. If I wanted to, I could write the next term, x to the 4th divided by 4 factorial, and these terms continue on to infinity. This is called a power series. It's a very important power series. We'll see exactly what this corresponds to in future sections. But this is a very important power series. I would encourage you actually, try pausing the video and try plugging this polynomial into Desmos. Take more and more terms and see if you can guess. See if you can guess what this polynomial starts to behave like. All right, for one more example, let's look at letter D. We have the sum from 0 to infinity of -1 to the n, x to the 2n plus 1 divided by 2n plus 1. So we're going to start with n equals 0. We have -1 to the 0 times x to the 2 times 0 plus 1. 2 times 0 is 0 plus 1, so this is just x to the 1, divided by 2 times 0 plus 1. There's my first term. My second term, now I use n equals 1, so -1 to the first. X to the 2 times 1 plus 1 is x cubed, divided by 2 times 1 plus 1, that's 3. Notice that the exponent here will be the same as the denominator. My next term is when n equals 2. If n equals 2, I have -1 squared. X to the 2 times 2 is 4 plus 1, 5, divided by 5. Let's write one more term, -1 cubed. X to the 3 times 2 is 6 plus 1, 7, divided by 7. And once again, this is an infinite series, so it keeps on going. But here are the first 4 terms of the expanded sigma notation. This series is another one that we'll see again, and it has a very useful and important meaning. Let's take a look at example 3. In example 3, we're essentially reversing what we just did in example 2. Instead of expanding out sigma notation, we want to take these series and convert them to a simplified sigma notation form. In each of these 4 examples, we're going to see a very important pattern that will appear later, and we want to understand the pattern and see how to create it using the shorthand sigma notation. The first pattern I want you to notice is in this first sequence. We have positive, negative, positive, negative, positive, negative. We have this flip-flop of the signs. And we saw this in example 2 with this example 2b. So we can create this flip-flop of the signs by using this -1 to a power here. So we'll see that for example A. In example B, what pattern do you notice here? Well, if you look at the difference between any two consecutive terms, the difference is always 3. 8 minus 5, 3. 11 minus 8, 3. 14 minus 11, 3. We have a constant difference of 3. So we'll see how to create a constant difference using sigma notation. And then in part C, we don't have a constant difference, we have a constant multiple. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 32. We'll see how to create that pattern using shorthand notation. And then finally for letter D, look at the denominators. I could think of having 1 over 1 to start with. So I have 1, 2, 6, 24. Do those numbers look familiar? Those are factorials. So in each of these cases, we'll see very important patterns, and we want to understand how to create those patterns in the shorthand sigma notation. So first, let's look at example 3a. We have the series 2 minus 3 plus 4 minus 5 plus 6 minus 7, and it keeps going. How can we write this using the sigma notation? Well, I'm adding up just n, really, starting at 0. Or starting at 2 rather. So I'm going to say I'm summing up n from 2 to infinity because this just keeps going. But I have this plus minus behavior. And I can get the plus minus behavior by taking -1 and raising it to the n power. At this point, I want to check to make sure that what I just wrote really is the shorthand notation. Because when I use this -1 to the n, sometimes this gives me minus plus minus plus. So sometimes it completely flips the sign around other than what I want. So I want to write out the first several terms to make sure that I'm getting the correct order of plus minus plus minus. So starting with n equals 2, I'm just going to expand this out to make sure that I get what I expect. So if n equals 2, -1 squared, -1 squared, that is positive 1. So -1 squared times 2 plus -1 cubed times, now n equals 3, plus -1 to the 4th times n equals 4. -1 squared is positive, so I have positive 2. -1 cubed is negative, so I have minus 3. -1 to the 4th, back to positive, plus 4. And then next one would be minus 5. So I get exactly what I want. I have the correct order of the plus minus plus minus. So this is very important. We can replicate this changing of signs, the positive, negative, by using -1 raised to the n power. If we were off here, if we had negative, positive, we could fix that by simply adding 1 to the power, and then the odds would be switched to evens, and everything would work out okay. So this is a very important pattern that we want to be comfortable with. The way to get the alternating sign is to use -1 to the n or -1 to the n plus 1. Let's work through 3b. For 3b, we have a constant difference between the terms, 5 plus 8 plus 11 plus 14, and this ends at 35. So between each of these terms, I have a constant difference of 3. 8 minus 5 is 3, 11 minus 8 is 3, 14 minus 11, 3. Everywhere I have a constant difference of 3. And I can replicate that in the sigma notation by multiplying by 3. I'm going to add up 3n, and if I just start with, let's say, n equals 1 here, my first term would be 3. I don't want 3, I want 5. So how can I change this 3 to a 5? I can just add 2. And now if n equals 1, I would start with 3 times 1 plus 2, that's 5. Think of what would happen if n equals 2. If n equals 2, then I'd have 3 times 2 plus 2, 3 times 2, 6, plus 2, 8. Aha, I'm getting exactly what I want here. So to get the common difference of 3, I multiply by 3 in the sigma notation. This is very important. To get a constant difference between the terms, I multiply that difference times n in the sigma notation. Sometimes I have to add a factor here or a term to make sure that I get the numbers starting where I want them to, but to get a constant difference, you multiply by that difference in the shorthand notation. Now this ends at 35, so I need to know what's my upper number here. Where do I end? So I want to know where is 3n plus 2 equal to 35? Well, this would be 3n equals 33, so n equals 11. If I go up to 11, then plugging in 11, I'd have 3 times 11, that's 33, plus 2 is 35. So this is a finite sum, it converges, And here's the sigma notation for this expression. With a common difference, a constant difference, we obtain that in the sigma notation by multiplying the constant difference by n. Take a look at part C. For part C, we don't have a constant difference between the terms, we have a constant multiple. So our series is 2 plus 4 plus 8 plus 16 plus 32. This series will diverge, by the way. If we keep adding larger and larger numbers, this does not add up to a finite sum. So instead of a constant difference, we have a constant multiple. This is called a geometric series, and we're going to explore geometric series in great detail. And the way to get a constant multiple here is to use a power in the sigma notation. So if we have a constant multiple of 2 from each term to the next, I can replicate that by having 2 to the power. So I'm going to have 2 to the power n, and my first term needs to be 2, so I'm going to start with 2 to the first. So n begins with 1, and then n goes on to infinity. It's an infinite series. So if n equals 1, I get 2. If n equals 2, I have 2 squared, which is 4. If n equals 3, that's the next increment, then I have 2 cubed, 8. So the way to get a constant multiple between the different terms is to use that multiple raised to the n. For 3D, we have the sum 1 plus 1/2 plus 1 over 6 plus 1 over 24. And I'm going to write this actually as 1 over 1, and my focus here is on the denominators. This is a pattern that we want to recognize. These are the factorials. We have 1 factorial, 2 factorial, 3 factorial, 4 factorial. The next term here would be 1 over 5 factorial, which is 120. So for this series, I have 1 in the numerator, and I'm dividing by n factorial in the denominator. N starts at 1, so I'm going to start from 1 and go to infinity. So being comfortable with this pattern, 1, 2, 6, 24, 120, recognizing those numbers as the factorial numbers is very important.